So this is a new unit, Mr. Dueck. How come it says lesson 5, not lesson 1? Actually, it's a continuation of the unit on work and energy. Everybody get the seating plan? Anybody not get the seating plan? Well filled in? Fairly neatly? Good. Yeah, that's going to be on YouTube. I break Unit 3 up into 2 subtopics. So I'm going to call this Unit 4, but I'm going to start with Lesson 5 because it does continue and I've never gotten around to changing the numbers. We're going to talk about one-dimensional momentum and impulse. In theory, Grayson, today is going to be all review of Physics 11 if you did momentum, but you kind of did that towards the end of the year. And then I'm going to build on that in Lesson 2. One of the most important concepts, Mickey, in all of physics is the idea of momentum. Newton first used this concept when he phrased his second law of motion. Actually, Newton never said F equals ma. He phrased it in terms of momentum, and I'll show you how he did that a little bit later on in the lesson. He called the product, hey, what does product mean? Adding, subtracting, multiplying, or dividing? Okay, he called, if you multiply mass and velocity, he called that the quantity of motion, but over the years now, we now call it momentum. Basically, it's the amount of motion an object has, and the amount of motion that an object has depends on 2 things: how fast and how much mass. How fast it's traveling and how much mass. Wait a minute, Mr. Dueck, that sounds like kinetic energy. It's very different from kinetic energy. What makes momentum so important is the fact that, like energy, it is a conserved quantity. The amount of momentum beforehand equals the amount of momentum afterwards. If I wanted to phrase that as a physics rule, Shaq, I would say, in an isolated system, a system in which no external forces interfere, the total momentum of the object in the system will remain constant. This is the law of conservation of momentum. Big deal. Actually, Josh, this one, while trickier than the law of conservation of energy, is often more accurate. In the law of conservation of energy, I was always ignoring heat. Here, I'll no longer have to do that. It'll take care of itself. It'll take care of itself. It's trickier, though, Mickey, because momentum, unlike energy, is a vector, not a scalar. We're going to be doing eventually more tip-to-tail diagrams than you can shake a fist at. The symbol for momentum, well, Rafi, we can't use M, so we use P for product, because M is taken for mass. And momentum is calculated by multiplying the mass times the velocity. P equals mv. You're going to start to notice, Jordan, that I'm going to be way more careful with my vector notation. I won't take marks off if you don't put arrows on, but I'm going to always remind myself, Zach, at every opportunity, momentum is a vector, momentum is a vector, momentum is a vector, momentum is a vector, which means I better be careful when I'm doing math and not do scalar math when I'm not allowed to. What would the units be? Well, what do I measure mass in, Josh? Kilograms. What do I measure velocity in? So the units are kilogram meters per second. Now, there is, Nate, a movement afoot to rename that. The same way as a joule per second is a watt, the same way as a Newton meter is a joule. There is a movement to rename this an Einstein. It hasn't happened yet. So right now, momentum is measured in kilogram meters per second. We haven't shortened it. And then the key idea. Momentum is a vector quantity. It gets its direction from the velocity, because mass is a scalar. Which means when you add momenta, which is the plural of momentum, you have to use vector addition. If everything's in a nice straight line, Shaq, you better let one direction be positive and one direction be negative. But as soon as you see norths and souths and angles, it's going to be tip to tail, tip to tail, tip to tail, tip to tail. And in fact, almost always, it's going to be non-right angle cosine law trig. And that we're going to get to in Lesson 2 and after Christmas. I told you that Sir Isaac Newton never actually said F equals ma. He gave his second law in terms of momentum. How? Well, I said Newton's second law can be rewritten in terms of momentum. We can start with F equals ma. And then it's going to be m times the definition of acceleration. What's the definition of acceleration? Well, change in velocity over change in time. That was what you were told way back in Science 10. What's change in anything? Final minus initial. So I can write this as m bracket v final minus v initial all over. I'm going to leave the time as a change in because time is that weird variable, Nate. It's always technically a change in because you're always starting and stopping a stopwatch. By definition, time has to be the final time minus the initial time. That's how much time elapsed because we're never truly starting at time zero. In real life, time zero would be when the Big Bang occurred, right? And then I'm going to go like this. I'm going to get mv final minus mv initial all over change in time. What is mass? Oh, sorry. Vector symbol, vector symbol, vector symbol, vector symbol. I should be fussy here because it's not a speed. It has to be a velocity. What is mass times velocity? What did I say in the box right above? I've scrolled down, but you have it there. What is mass times velocity equal to? Momentum. So what is mass times final velocity equal to? Momentum. Okay, so this is really momentum final minus momentum initial all over change in time. And what's final minus initial the same as? Here is what Sir Isaac Newton gave his F equals, his Newton's second law. He wrote it this way. F equals the change in momentum over a change in time. It turns out that's F equals ma in disguise. That's a more complicated version. In many ways, it's a more descriptive version. Here's what it really says. If you change an object's momentum, the force is the rate at which you're changing its momentum, because we said if you divide by time, that's the rate. In other words, a force is how fast you're changing an object's momentum. That's how you can calculate the force. Not needed to do that. It's a complicated concept. F equals ma is certainly more straightforward. So Newton's second law can be stated in words in terms of momentum is as follows. If you have an unbalanced net force, that changes the motion so that of the object, so that the rate of change in momentum is equal to the unbalanced force. Or F equals the rate of change of momentum. Where momentum is mass times velocity. That's the first equation that you have on your formula sheet in this unit. Momentum is mass times velocity. And there's only one more equation. You're going to get it in about 30 seconds. The rest of this unit is all applying it, applying it, applying it, applying it. The second equation talks about impulse. What's impulse? Well, if I take this equation and I times the t over to the delta t over to the other side, I get, geez, how about not crossing it out, Mr. Dueck? I get that. The change in momentum, delta mv, equals f delta t. Turns out we have a name for this. Rafi, we call this impulse. And impulse is defined as change in momentum. Grayson, what's impulse defined at? No, I picked on you for the normal force. I got to go to somebody else. Jenny, what's impulse defined as? Whenever I see the word impulse, what can I think? No. Change in momentum. When I see the word impulse, what is it asking me to find? When I see the word change in momentum, what else could I use instead? The word Impulse. What's impulse? I'm doing this for a reason. I'm picking on you, but I'm doing this for a reason. Because every year, and on your test on momentum, I say to kids, find the impulse. And they leave it blank. Now, if I had said, find the change in momentum, Jenny, what's change in anything? They would all know to find the final momentum, find the initial momentum, and subtract. I'm not going to do that. I'm going to say, find the impulse. And when I say find the impulse, Jenny, what's impulse the same as? And what's change in anything? Final minus initial. That's the three-link chain you do need to commit to memory. It's one of my, you want to irritate me on this test? Leave the impulse question blank because you forget that impulse is a synonym, is interchangeable with change in momentum. Those of you that are Star Trek fans, remember what they called the engines that they used to move the Enterprise? Impulse engines. When they were moving the spaceship, impulse engines changed its momentum. Did they change the mass of the Enterprise? No. They must be changing the velocity, and that's how they're moving the ship around. Now, they never got into the physics of how impulse engines worked, but at least the terminology, Mickey, I could live with that. Okay? You made it? He's got the notes for you. There are several ways to change the momentum, to exert an impulse. You could do, if you look at this equation, Jenny, a big force acting over a short time, baseball bat hitting something. A small force acting over a long time, if you gently nudge something, but you keep pushing it and keep pushing it and keep pushing it, eventually you'll have changed its speed quite a bit if it's an unbalanced force. The biggest changes in impulse are big forces acting over a long time, like a rocket engine, say. What are the units? Well, momentum has measuring units which have dimensions of mass times velocity, but impulse is force times time. What do I measure force in? What are the units? So let's write down newtons times. What do I measure time in? Seconds. But I'm going to make an argument here. Newton is force. What was the basic definition of force that you learned in Physics 11? F equals what? MA. M is mass measured in kilograms, and A is acceleration measured in. So I'm going to argue that Newton is actually a kilogram meter per second squared. So a Newton second is a kilogram meters per second squared times a second. What do you notice? How many S's on the top? 1. How many S's on the bottom? 2. One of the S's cancels. And what I want to convince you of, Mark, is it turns out a Newton second is the same as a kilogram meters per second. It's momentum. It's momentum. Which one is correct? I'll be honest. If I've gone mass times velocity in my work, I'll probably write kilogram meters per second because in my brain is mass times velocity. If I've gone force times time in my work, I'll probably write Newton seconds. But whichever one you use, Zach, I won't be fussy. I'll give you credit for it. I'll just try and do it properly as far as I'm concerned. The law of conservation of momentum says this. The total momentum of an isolated system of objects will remain constant. We can do better. Turn the page. Seeing as you've all flipped the page over, can I give you some advice at the top? Let's write down our momentum equation. Momentum equals mass times velocity, because we're going to be flogging that to death quite a bit. You can also write down our impulse equation. This is the second equation that's on your formula sheet. Does it say on your formula sheet F delta T equals delta P, or does it say F delta T equals M delta V? Anybody have the formula sheet handy? Zach has it right in front of him if he bothers to look at it. I got the F delta T on the right hand. Does it say delta P, or does it say M delta? Doesn't say M delta V? Okay. Those are the two equations for the whole unit. Okay, we're done. Your test is tomorrow. Well, no. It's all going to be now looking at ways to use this. But again, notice, Mickey, I'm being very careful with vector notation. Example 4 says this. If conditions are such that the car and truck end up at rest, you know what, Rachel? I would probably underline the word at rest after the collision. How can we say that the momentum has not been lost for the system? So here is after. How fast is the truck moving after the collision? 0. How fast is the car moving after the collision? So what's the total momentum after the collision? If momentum is mass times velocity, and both velocities are 0, so let's write here, final momentum is 0. You know what that means, Jordan? What was my initial momentum before the collision? It had to have been 0. Wait a minute, Mr. Dueck. You've got things moving. How the heck can it be 0? It is. Well, before the collision, what's moving? The truck, the car, or both? Stuck together or separate? So let's write down momentum truck initial, vector sign, plus momentum car initial, vector sign. Momentum is what times what? So this is going to be mass of the truck, V truck initial, mass of the car, V car initial. What is the mass of the truck? 2,400. What's the velocity of the truck? 10. Plus, what's the mass of the car? 1,000. Listen carefully. What's the velocity of the car? Why negative? Okay, we have to pay attention now. And I've cooked these numbers up, but I think you get 24,000 plus negative 24,000, which gives you an initial momentum of what? Which I knew because what was my final momentum? 0. It does work. This is the law of conservation of momentum. It can be written in several ways. You can say the momentum of object 1 beforehand plus the momentum of object 2 beforehand equals the momentum of object 1 after plus momentum of object 2. That's too much writing for me. The one that I prefer, Grayson, is this one. This is my, remember in forces, this is a job for a free body diagram. Remember in our last unit, is there a change in height? Is there a change in speed? This is a job for yucky curvy path. This is a job for conservation of energy. This is my fallback for this unit when there's a collision or an explosion. Now, you have to know what that symbol means. Does anybody know what that symbol means? It's an abbreviation. This means the total or the sum of. So what that says very concisely is the total P momentum, I initial, before, equals, has to equal, the total momentum after. That's the shortest and clearest and most fundamental way I can write it. I always start out writing that when there's a collision or an explosion, and then I adapt it by knowing that any one momentum is mass times velocity. Mass times speed? No, mass times velocity. If you expand it, you get that. You know what? That's too much writing. My fallback is this. Short, sweet, even uses a Greek summation letter, so it looks kind of nerdy. Mac, that's dear to my heart then. Mac, we use conservation of momentum when there is a collision or an explosion. In fact, if you want my shorthand version, Mickey, we use conservation of momentum when there is a jeune. Whether it's a collision or an explosion, that's a job for conservation of momentum. Let's look at an example. Example 1. A rifle bullet of mass 0.06 leaves the muzzle with a velocity of 6 times 10 to the second meters per second. If the 3-kilogram rifle is held very loosely, with what velocity will it recoil when the bullet is fired? Rob, what's this question asking me to find? Velocity or speed, first of all? Velocity, which suggests a vector, not a scalar approach. Don't try energies. Okay? Is this a collision or an explosion? I think shooting a gun qualifies as a controlled explosion. You know what this is a job for? Conservation of momentum. Soon as I think that little line of reasoning, first thing I write is this. The sum of all the momentum before equals the sum of all the momentum after. By the way, the summation symbol when you typewrite it looks like that. When you're handwriting it in a hurry, it starts to look an awful lot like a capital M on its side, and I'll figure out what you mean. I usually don't add the little wings because that's just too much extra work for me. So, Rob, I want you to imagine someone firing a rifle. Before you pull the trigger, what's moving? The rifle, the bullet, both, or neither? Neither. So what's my momentum before I pull the trigger? Bang! I pull the trigger. After I pull the trigger, what's moving? The rifle, the bullet, or both? Stuck together or separate? Separate, so I'm going to go like this. Momentum rifle final plus momentum bullet final. That's how we'll start out even the yucky vector angle questions. Then I always pause. So I've broken it down into its constituent parts. Then I pause and I say, looking at this question, does it mention angles or norths of souths or thetas or anything like that? No. Then I'm just going to let to the left be positive and to the right be negative. If it mentioned angles, I would dulp. I would dulp. And the level of difficulty goes up astronomically. But, Grayson, no angles mentioned? Okay. Momentum is what times what? What did we write at the top of the page? If you were listening to my instructions. Sorry? Momentum is what times what? Mass times velocity. So I think, Zach, the momentum of the rifle final is going to be mass of the rifle v of the rifle final. Plus momentum of the bullet final, I think since it's mass times velocity, Shaq, is going to be mass of the bullet v of the bullet final. Rob, what did you say we're trying to find? I don't think we want the velocity of the bullet. The rifle, the recoil velocity. Does this have angles or anything funky like that? Then I can just get the VRF by itself. I think, Rob, the first thing that I would do is I would minus this whole thing to that side. I'll get negative MBVB final equals MRVR final. What did you say we're trying to find, Rob? How would I get that by itself? Mass of the rifle, yeah. So the final velocity of the rifle is going to be negative MBVB final divided by mass of the rifle. Let's plug and chug. The final negative 0.06 600, and I tried to make these numbers reasonable. I did some Google searching. 3 kilograms. The bullet's going to go forwards at 600 meters per second. How fast is the rifle going to go backwards? What do you get? I could probably do this in my head. 12? 12 even? Pardon me? Wow, Rafi, what? What's the negative telling me? That if the bullet went to the right, which way did the rifle travel? To the left. If the bullet went backwards, the rifle went forwards. Units. Now, before we turn the page, let's take a look at this, firing a gun. What if it was a heavier bullet, a higher caliber? What would happen to the recoil velocity of the rifle? So if this number got bigger, would the recoil velocity get bigger, smaller, or stay the same? Bigger. In fact, if you look at artillery shells, which have a huge mass, they have a crazy artillery recoil as well. You need a tank or something. What if I wanted the bullet to travel faster? What if I use more gunpowder? What will happen to the recoil of the velocity? Bigger, smaller, stay the same? Bigger. This is the difference between shooting a .22, shooting a shotgun. Okay? What if I have a really, really big gun and I want to try and lower the recoil velocity? I could mount the big gun on a tank so that instead of a rifle that weighs 3 kilograms, it's attached to a tank that weighs several thousand kilograms. That's going to give me a smaller recoil of the tank. Oh yeah. You going to make it? You're not looking good. You're doing the dozy thing. Next page over. Football players. Got a few of you here. What is the momentum of a 112 kilogram football player running at 4.8 meters per second? Shaq, what's this question asking me to find? Read A, please. Momentum. Oh, momentum is mass times velocity. Let's start there. 112 kilograms, this is about 260, 65 pounds. You know what? Rob Gronkowski. He's built about right because he's fast. 4.8 meters per second. That's not really, really fast. That's not really, really slow. That's pretty fast. How much momentum does a player like Rob Gronkowski have? Well, it's going to be 112 times 4.8. And Shaq, you play football, right? Okay. Would you be thrilled about tackling Rob Gronkowski? Be honest. Would you be thrilled to have to be tackling him to try and save your team's lead? Would you feel really confident? Say no. Why? He packs a lot of momentum. Okay? And that momentum, like energy, that momentum also has to go somewhere, but it's also a vector. So I'm going to write 538 to 3 sig figs. Units, kilogram, meters per second. Shaq, I know you're my football guy. So actually, no, Mark, did you play football?
Yeah, I didn't like play.
Okay. Rob, what does B want me to find? Impulse, which is another word for what? Okay, now I have 2 options. Don't write this down yet. I can either find impulse by going change in momentum. Don't write this down yet. Don't write this down yet. Or I can go force change in time. Looking at the information that they've given me, have they given me a force anywhere in the question? A force in newtons? No. Have they given me a time in seconds in the question anywhere? No. In fact, in part C, what are they asking me to find, Rob? You know what? Then I'm not going to use this. I think in part B, I'm going to use the fact that impulse is change in momentum. What's change in anything? I see why he didn't get in the game. A little slow. Uh-huh. By the way, if we're tackling, now this is Shaq assuming you're tackling head on. Angles, another lesson. But for now, we're tackling him head on. What's his final momentum going to be? Rob, if you tackle anybody, what's the final momentum that you want them to have? Minus. And what was his initial momentum? We just figured it out in part A. 538. In your head, Rob, what's 0 minus 538? So the impulse, if you're tackling him, you have to cancel out his momentum. You have to give him an impulse of negative 538 kilogram meters per second. What's the negative saying? If he's running north, which way had you better hit him? South. If he's running east, which way had you better hit him? Or if he's running forwards, you better hit him in the backwards direction. So you can hit him head on with you running forwards as long as you're facing in the opposite direction. C. We'll go back to Shaq tackling Rob Gronkowski. And we're going to assume it's going to take Shaq a while to bring Gronkowski down. In fact, I'm going to assume that Gronk keeps rumbling, sort of like Marshawn Lynch does, dragging tacklers, and Gronk does too, for 1.2 seconds. But he's losing momentum the entire time until he comes to a stop. Shaq, what does part C want me to find? What does part C want me to find? I got to be careful. I put a word in front of it on purpose. And the reason is I suspect that if you were tackling and he was dragging you, your force isn't constant. I suspect you probably, it's bigger right when you hit him and then you kind of, anyways, average force. What did we just find, Rob, in part B? Impulse. Hey, is there an equation that has impulse and force in it? The second equation for this unit. Impulse is force change in time. Shaq, what did you say we're trying to find here? Can you get the force by itself, please? So the force is going to be the impulse divided by, and I'm going to drop the delta now because T is always a delta and I'm lazy. What was the impulse? Negative, and you know what? Instead of saying negative 538, I'll use the extra sig fig, which was negative 537.6 divided by, Shaq, how long did it take you to bring him down? How long did it take you to bring him down? No? So you went like this. You get negative 448 even? I used the actual answer button. What's the negative telling me? The force that you apply has to be in the opposite direction of his acceleration and momentum. So, head-on collisions. Now, before we move on, how could you apply a bigger impulse? Well, momentum not only is, change in momentum is not only force times time. What's our basic definition of momentum? Momentum is what times what? Mass times velocity. If I have a bigger mass, like a lineman, I don't have to be moving as fast. I can have a smaller velocity and still give Gronkowski an impulse of negative 538. It's why there's a reason why all the linemen put on bulk. That extra mass helps. If you can put on 40 pounds and not lose much speed, it's a fair trade-off when it comes to collisions. So if you watch the NFL, I'm assuming most of you have watched a football game somewhere along the way. Football, good physics. Example 3. Here's a very famous physics thought experiment. You're doing a spacewalk outside the space shuttle, except you're using your rocket pack. There's no cable that's attaching you and the shuttle. Your small maneuvering rocket pack suddenly quits on you. Uh-oh. And you're stranded in space with nothing but a $50,000 camera in your hands. How can you get back to the shuttle? Now, this is purely a thought experiment because in real life, the shuttle would probably have 3 rocket packs, a backup and a backup for the backup, and you would just radio and your crewmate would come and get you from the shuttle. But let's assume as a thought experiment. Zach, what were you suggesting? I heard you say more specific. It's a vector, so I need a direction. Throw it which way? Throw it, yeah. Throw it in the opposite of the shuttle. Why? Before you throw it, what's the momentum of you and the camera? 0. After you throw it, what must be the momentum of you and the camera? Still 0. So if you give the camera a positive momentum, now you have a bigger mass, your velocity will be much slower. The camera will go shooting off if you give it a good heave, but you will slowly move in the opposite direction. Okay? A bad understanding of momentum is what a lot of the Kennedy assassination conspiracy theorists have. If you watch, and it's a tragic event, but if you watch the Zapruder film, when John F. Kennedy gets shot in the back of the head, his head moves back. And people say, oh, that's impossible. He must have been shot in the forehead. There must have been a second gunman. Sorry to be a little graphic here, but his head moved back because some mass went forward. Yeah. Okay, his brains went forward, and that was enough to rock his head back. The net momentum was still 0. Not breaking any laws of physics there. Sorry, but I have a brother who's a conspiracy theorist, and I just... And the Twin Towers were blown up. The planes couldn't... Trust me, there's enough kinetic energy and potential energy in that fuel that the towers would come down. Okay? Rockets. Rockets are great examples of momentum. A rocket expels 1.2 times 10 to the third kilograms of gas each second, and the gas leaves the rocket with a speed of 5 times 10 to the fourth meters per second. Will the thrust produced by the rocket be sufficient to lift it if the force of gravity on the rocket is that much there? Okay, Josh, what's this question asking me to find? Thrust. I think thrust is force. So what I'm going to do is see if I can calculate the force, and it better be bigger than gravity. Otherwise, this rocket's not getting off the ground. Now, maybe I could go F equals ma and blah, blah, but I see a speed. I think what I'm going to try and do is I'm going to try saying, hey, maybe let's try writing that. Impulse equals impulse. On the left-hand side, I have a delta P, which is a change in momentum. Jenny, change in anything is what? So I can write this as momentum final of the rocket gas minus momentum initial of the rocket gas. That equals F delta T. I think, Naomi, we're going to assume that the gas starts out at rest before you turn the rocket on. I think that's fair. So we actually end up with this. Mass of the gas, velocity of the gas equals F delta T. Now, what did you say that they were asking me to find, Josh? Which in this equation is what? Sorry? No. Which variable is it in this equation? Force. So normally I would divide by delta T, but read the question very, very carefully. How much time are we talking about in this question? 1 second. So I'm going to divide, and then it's going to just vanish. It's not that somehow time canceled. It's dividing by 1 isn't going to change your answer at all. So I am going to write over here, the force, I guess, is mv over delta t, but it's going to be over 1 because it says 1 second. What's the mass? 1,200. What's the speed? 50,000. 5 times 10 to the fourth. Will that get this rocket off the ground? If gravity is pulling down at 5.8 times 10 to the 7th, what do you get? Do you get 6.0 times 10 to the 7th? Is it 6 times 10 to the 7th? So I got gravity pulling down. If I did the free body, gravity down 5.8 times 10 to the 7th. Thrust up 6 times 10 to the 7th. I have 0.2 times 10 to the 7th newtons left over. That's what's going to go into causing this rocket to accelerate and leave the ground. Yes, get off the ground. Let's get off the ground. Example 5. Example 5. A 3.5 kilogram cart traveling 1.2 meters per second collides with a stationary 1.8 kilogram cart. You know what? There's my trigger word. This is a collision. Now, we've done a couple of questions using impulse, but what did I say? When it's a collision, what's my first instinct? What's my first approach? I start out with conservation of momentum. So the fact that this is collision and it wants me to find a velocity, I'm going to start out by saying the sum of all the momentum before the collision has to equal the vector sum of all the momentum after the collision. Now, here's what we're going to decide, just so all of our work looks the same, Eric. As we read, the first mass we run into, we'll call mass 1. I'm going to call mass 1 the 3.2. This next mass we run into, we'll call mass 2. The only time we won't do that is if the diagram, you're saying I wrote initial twice, Jordan? The only time I won't do that is if the diagram labels the masses a certain way. I'll go with whatever the diagram says. But if they don't give me a diagram, my fallback is whatever I see first is the first mass. Before the collision, what's moving? Mass 1, mass 2, or both? Mass 1, so I'll have momentum 1 initial. Bam! They collide. After the collision, what's moving? Mass 1, mass 2, or both? Both. Stuck together or separate? So I'm going to write momentum both final. And here I always pause and I ask, are there angles in this question? Are there norths or souths or anything like, or is this in a nice straight line? If this is in a nice straight line, then I'm going to let to the right be positive, to the left be negative, and I'll interpret it that way. Okay. Momentum is what times what? So momentum 1 initial is going to be mass 1 v1 initial. What about the momentum of both? How would I write that? I think I would say mass 1 plus mass 2 v final, because if they're stuck together, they must be traveling at the same velocity. What are we trying to find here? Which will, oh, VF? How would I get the VF by itself? Divide. VF is going to be M1 V1 divided by M1 plus M2. Now, write that and then put your pencils down for a second before we move on. So here's car crashes. Ready? If the first car was heavier, how would the wreckage move off? Faster, slower, or the same speed? If this got bigger, how would that affect the wreckage? Faster. Or if the first car was coming in faster, how would the wreckage move off? What if the second car was larger compared to the first car? Would the wreckage move off faster, slower, or at the same speed? So this gives you an idea sort of some using principles of physics kinds of questions I can ask, but also it gives you, oh yeah, I kind of figured that out about car crashes. I've seen enough in the movies, but there's the physics behind it. Now let's plug and chug it. Mass 1, 3.2, 1.2. Wham, they collide. 3.2 plus 1.8. Again, I see a lot of kids write this and then they do it wrong on their calculator. I would strongly encourage you to practice these on your calculator. And you should get an answer of 0.768 meters per second. What if the answer had been exactly 0? What would that mean? They hit and stuck together. In this question, that would be impossible because I have momentum before, so I have to have momentum after. What if I got a negative answer? Yeah, okay, that would be if we had a head-on collision, but the second car had more momentum. It would cancel out the first car's momentum, and they would go back in the opposite direction. And whoever was in the first car probably would suffer a fair bit of damage. I keep meaning to nuke number 6, and I always forget. I'm not a big fan of it. But I like number 7. I like number 7. Example 7 is a nice question. A 1.2 times 10 to the third kilogram car traveling 33 meters per second collides head-on with a 1.8 times 10 to the third kilogram car traveling 22 meters per second in the opposite direction. If the cars stick together, what's the velocity of the wreckage after the impact? Mac, is this a collision? You know what this is a job for? What? First thing I'm going to write is the sum of all the momentum before the collision equals the sum of all the momentum after the collision. Then, Nate, I break it down further. I read the question and I say to myself, before the collision, what's moving? Mass 1, mass 2, or both? Both. Stuck together or separate? So I'm going to have momentum, change colors, Mr. Dueck. Momentum 1 initial plus momentum 2 initial. Bam! They collide. After the collision, Jordan, what's moving? Mass 1, mass 2, or this is one of my favorite units to teach, and you're seeing why. Jordan, after the collision, what's moving? Mass 1, mass 2, or both? Stuck together or separate? Okay, I've broken everything down into its individual momenta. Now I pause. Are there angles? Are there norths of souths? Are there thetas? If there was, underneath each one of these, I would dope a little vector. In fact, I'd draw 3 vectors, and then I'd add the first 2 together, tip to tail. Are there angles here? Okay, then we can break this down. Momentum is what times what? It's going to be mass 1 V1 initial plus, bet you're awake now though, mass 2 V2 initial equals, since they're stuck together, it's going to be M1 plus M2 V final. Nate, what are we trying to find here, kiddo? They're telling us the cars stick together. Yeah, which one of those? Because there's 3 in my question. V1 initial, V2 initial, or V final? V final. Okay. By the way, I could have given you V final and said, hey, how fast does the first car go? That's what the RCMP do when they're investigating an accident. They want to know how fast the initial car was going, right? Nate, how could I get the V final by itself? How could I get this by itself, kiddo? What would I do with this bracket here? Yep. So I'm going to have this. V final is going to be M1 V1 initial plus M2 V2 initial, all divided by M1 plus M2. Hey, it's plug and chug time. What's mass 1? I'm going to write 1200 because that's faster than writing 1.2 times 10 to the 3. What's velocity 1? 33. What's mass 2? 1800. What's velocity 2? Opposite directions. Negative 22. And you can see if I gave you this as a multiple choice, absolutely one of the answers would be if you put a positive there. Absolutely. Divided by 1200 plus 1800. You get kind of a neat answer here because I cooked the numbers very carefully. What do you get? You get exactly 0. This would be an example of a collision head-on. The second car is bigger, traveling slower. The first car is smaller, traveling faster. And it's exactly enough that they cancel out each other's momentum. The final momentum is 0. You know what that means? What was the initial momentum? 0. Now this is the velocity, meters per second. I'm going to pause here. You can work on your energy review, any other homework, because your test is next class. We're going to pick up with this next class Friday, which is a late start Friday, so I figured I'd spend the second part of this lesson there.